Yeah. Okay. So today, I wanted to take this opportunity to present some topics which I think would be important, especially for the PhD students. So it's mainly some basic necessities for you to understand some of the work that Linus is doing. Since I'm a student, then I'm mainly focused on that. So I will talk about. I'll just start with some basics, like what is a sigma model, and I introduce some sigma models, and then I'll talk about integrability, and then introduce integrability of the sigma models that I'll introduce, and then in the end I will just give some short overview of what work I've been doing, what Linus has been doing, and what some other people have been doing in this. So just to get like a basic overview of everything, I won't go too much into detail. I've done a similar talk like this, I think 2 years ago. It's on YouTube, but the video and audio quality are not so good. So you can also check that, but yeah, the quality is at like 100 pixels, so it's, we were not so good at recording back then, but it should be fine now. So you can also check that. I'll try to not have big overlap with the previous talk, but some parts will be the same. So the basics are from 2 lectures I've been part of 2 years ago. So there are lectures about integrability and integrable deformations. And they're available on archive, so if you have a tablet, you can just search it up and follow with it. So this is a lecture about something called integrable deformations, which is if you have an integrable model, you can deform it and ask whether the space is integrable. So it is a part of what I'll be talking in the end. And the other is just the lecture on integrability. So you can check those out. They were part of this summer school, which I went to called integrability of these informations. It comes in it's every year, so you can also attend one and one. So today I'll start by talking about sigma models, what is sigma model, and then we'll go into integrability. So at least when I first started learning about this, I thought it was confusing, and it still is because it is such a very generic name for a lot of different models. So if you just come with some particular examples, then you may be confused on how they are connected. But the basic setup is actually quite simple. The problem is that there are just so many options for what this can be that anyone can get confused. So you have a map between 2 spaces. They are usually called the source or the worldsheet and the target space, depending on whether you run in string theory or not. This can have many setups. I will use some notation. I will use sigma because this will usually be a 2-dimensional surface and metric h. And so they are all preeminent spaces with metrics that don't have to be constant. And I'll call the map by like a scalar field, which this can have multiple dimensions. Like the dimensions of these are not fixed yet. So let's establish some coordinates. So on this space, I'll call these coordinates xi. So I goes from 1 to the dimension sigma, which we don't know what it is yet. And on the target space, I'll use the Greek indices. So for example, mu and mu goes from 1 to the dimension of the target space, which I call n as a manifold. It can also be T, but then T is usually for the dimension space. There will be some confusion. And so the main characteristic of what the sigma model is that it comes up with equivalent action, which is quadratic in the derivative of the field. So that is like the most the main property of the sigma model. So you are integrating over the source space, so over I'll call this D like I mentioned, over the axis. And on the source space, you have the metric H. So for your volume form to have the right Lorentz transformation properties, you need this vector. And then what you just do, you just take the quadratic so the quadratic term with derivatives, the kinetic term, and you assume that your matrix don't have to be constant. So you write down this. So this is the sigma model action. It's like a characteristic of all the sigma models. And now the confusing point comes from you can have various choices of what the target and source space is, and you can cover a big range of different theories. So for example, you always want your space-time to be somewhere, so it can either be here or here. And then we will call different theories like target space theory or worldsheet theory, depending on whether the space-time sits here or here. And I'll try to go through some examples so that you understand what is what. But first, let's talk about this very generic theory. The equations of motion, you can calculate them with respect to derivatives of this. So you'll get something like this. Now I will use downstairs indices to denote derivatives because it's a longer expression. So I'll just shorten it by moderating the derivatives. So this is the equations of motion, and these are the Christoffel symbols, and for this very generic equation that both spaces can be curved, both spaces have their own curvature and the Christoffel symbol. So I know which one belongs to which by the left index, the left operations. And this is an equation that comes from usually you will only have one of the space be curved. And then this sort of combines the both options. So here these first two terms, so imagine if this is zero, the target is not curved, then this is just the Laplacian. So you have something like a wave equation, for example. And
maybe something that is a partial derivative in action or in DI.
Or
Because
I feel like in action it doesn't matter. No?
Where does the Christoffel symbol come from?
Well, they come from this metric being dependent on pi. Right, so this metric is on the target space. The coordinates of the target space are this map phi. So you can do derivative of this metric with respect to this pi, and you can do derivative of this metric. So this metric has these ij indices, right? So it makes sense to write something like this, because the metric is dependent on the fields. And the same for the other metric, it makes sense to do something like this. So you take this action, you vary it with respect to this field pi, and you just do like a generic variation of this action, and then you have your you can do something like this: d phi mu is di phi mu delta x. Right, so you just do a variation, and then you pull out all these delta x times in front, and then you get your equation. So, this g depends on phi, so will depend on this x through this relation, and you will have some derivatives of this g, and they symmetrize in such a way that the crystal will disappear. And same for the h.
Another way of saying it is that phi is scalar. Well, partial derivative and right derivative are the same.
Yeah. Oh. And so in the end, you end up with this equation which combines these two possibilities. This is like the Laplace equation, and this is the geodesic equation. So this is something like a mathematician's description of what the sigma model is. You have this very generic setup. All you need is this quadratic action, and then you have different choices for the spaces and the metrics, and you can get a lot of different theories, which I'll now try to show you some of them and show you that it's just all comes from different choices of this and G sigma. So first, just the statement, the name sigma model comes from the paper by Bjorn Levin, called axial vector current and beta decay. So they were studying some particle physics, some parallels and scalar mesons. And one of the scalar mesons was called the sigma meson. So just from that, that's the name why it's called the bound. Example. So one of the main examples. So either you usually have two options for the model, either it's a worldsheet model or a target space model, and then it depends on where the Minkowski space is situated. So if the Minkowski space is the target, then you will call it the worldsheet model, and if the Minkowski space is the source, then you will call it the target space model. And I'll show you some examples. So a worldsheet model, I'm saying worldsheet instead of source because we are usually dealing with string theory. So with the string signal, string theory. And that is for dimension of this space equal to 2. And it is given by the standard Polyakov sigma collection. So the setup is that you have here you have just a coordinate space in the source, and you're mapping so there might be some confusion because in the generic mathematical version I just use phi as a scalar field, but in strings you just use x for the map. So hopefully it's not very confusing. So this is the target space with some space-time. So this is the space-time, Minkowski space-time. At least some part of it. Usually, in string theory, you have more dimensions, and you presume that space-time is somewhere there, and extra dimensions are compactified. So this would be, space-time plus internal manifold. And the action. At each action, you have some factor, some prefactor, which has some physical meaning, some dimension, some constant. So here is this alpha prime constant or Regesol. You encounter it when you study this Polchinski book or some other books. And then I'm also changing the notation because I'm just using the usual one. So for this worldsheet coordinates, I'm using mu, and space-time, I'm using mm. So this is the standard action. and with the metric on the source I call H. So for the metric I'm speaking with the same numbers, with the same notation. But also, so a string theory in general is some sort of generalization of the notion of a sigma model, because you don't only have this symmetric quadratic action with the metric, you also have an antisymmetric piece with something called the B field. So it's just a slight generalization of what of the notion of sigma model by adding this antisymmetric. So this is both antisymmetric and antisymmetric. So in the I mean, so this quantity overall is symmetric. It's just the kinetic term, right? So if you exchange mu and u and MN, it has to be symmetric, which can be either done by having two symmetric tensors or two antisymmetric ones, because minus times minus is equals. So it's fine. If you want to do like something like epsilon times g, I mean that's just zero. And then you can also have the string background, so you can also add the dilator edit this way, like a quantum correction. So this serves as an H bar parameter, like in quantum mechanics, and the more power it has in the action, then it's higher order connections. So yeah, you will see this string sigma model a lot. You will get explanation for what this is when you study Polchinski and some properties of this. I'll not go into detail here, but so the reason this is called the worldsheet theory is you always you need to care about where you integrate, right? You integrate out over this two-dimensional worldsheet space, so this is why it's called worldsheet theory. So something that would be a target space theory would be called this supergravity action. Yeah, I'll get to that in a minute. First, I'll just say one more thing, and then this theory has Weyl invariance, which means that it is it is a symmetric with respect to rescaling of the metric. Yeah, H.
Yeah, so the standard, the metric in space-time is not big G. You just wrote
Yes. Yeah, so I changed this. I mean, it doesn't matter which you change. Yeah, because I'll use small g for something else. So yeah, but you have Weyl invariance, which means that we can multiply this by some positive function, and these two contributions cancel out only in 2 dimensions, because the determinant scales with the dimension. So this scaling of the metric is dimension dependent, and this scales to the minus first. So this cancels out only in 2 dimensions. So just to tell you what the target space theory is being. So you can imagine that you can build another type of map or space over this. So you can completely forget where your string comes from, how it's parameterized. And you can just look at this space-time and you can build another space over here. So in this case, the space would be space of tensors. So you have some tensors here. And which ones I mean are just the G, D, and phi. So I'll have some background fields. We call them background fields. The metric, the big field, and the dilator. And they just depend on this string parameter x. So now you can consider some action in which, so here the main fields were the sigma and tau, and then x depended on sigma and tau. And these g and these were just the geometric parameters of the theory. You could also argue that the action depends on the stage, and you can variable basically stage, so that the main field is X. And but we can consider another theory where these main fields would be G, B, and phi, and they all depend on just on this X. And of course, X has to be parameterized on the virtual somehow, but you don't need that. And you can then you can integrate over these X's. So then you can make some target space actually. So this is called low. I'll integrate. I'll just use the bottom theory case for integrate over 26 dimensions. And so this is the main difference in theories, right? What you're integrating with respect to.
But the way you define things, it sounds like you're still talking about sigma models.
Yeah. It sounds like that, and I'll show you in a second why this is not a sigma. Yeah.
The dimension 26
Yeah.
comes from the Lorentz invariance,
Yeah.
but for the open or closed,
So it's the same. For this. Yeah. There's differences in open and closed, but not in the dimension of the space. This H is D, so HI. Okay. 3 times. So the D field is like some field strength, and this is so the D field is some gauge field, and this is like a field strength of that gauge field. So you know that from electromagnetism, but this is the same case, it's just one index more. And then you have this field. So this looks like a sigma model, right? Except for, what we call sigma models should be dependent on the definition, and that the definition is that the action, so this is basically the definition of the sigma model, that the action should be quadratic in the fields that you're considering. So we're considering this GB and phi to be now our main fields. I did it to distinguish the difference between the source and target space theory. But this is not a sigma model because the way on how this action depends on this field is through these geometric quantities like the square of the field strength and the H scalar, and they are not just second derivative of the metric. There's a more complicated structure. First of all, it's a scalar, so you need to contract the matrix somehow, and you don't just contract it like that. So this is not a sigma model. It is a sigma model in the dilaton. This is just a normal sigma model definition, except for this function like this. So I mean, yeah, it's not a sigma model even in the dilaton because of this contribution. But this is something that you would call a target space.
You can redefine that, but I still don't. I'm not sure if I would agree that it's a sigma model.
For the dilaton.
Even for the dilaton.
Yeah, I'm saying it's different than a sigma model here. I'm just trying to showcase what like the target.
So okay, it's a bit mixed up because the metric. If you're thinking about the sigma model, there is a metric.
Yeah.
But for the dilaton, the metric is not G.
Yeah. So this is just
no, and not those coordinates either. So there's
there's
a
no
straight down one dimensional metric.
Yeah, exactly.
So I don't know how useful it is to
So this is
There's also another terminology. People talk about linear and non-linear sigma models.
yeah. So you could also see that.
But that's a different. I guess that refers to whether the metric target metric depends on the fields.
Yeah. I'm not completely sure what the difference between symmetric and non-symmetric.
I didn't say that. I said linear and non-linear.
I think it's just so you can also have the potential here, right? So if you have some non-linearity, or the respect to how the metric depends on the fields.
I think so.
So if the metric does not depend on the fields at all, it's some diagonal metric, then you would call it a linear sigma model. And if it depends on the fields, then it's a non-linear sigma model. That's how I understand it. I'm not sure if it's That's the right terminology.
I think with the potential is not the signal.
Yeah. So let's have a look at some proper target space signables. So now I introduce some more signables, and there will be what we call target space different to that object one. So one important one or one useful one is called the Owen signal. It's used, for example, in particle physics and in solid state physics. So you have two ways to define this. So you have your map. So that's the most important thing. And now this M is acting as a source. So you have your space-time, so let's say 4-dimensional or 2-dimensional, and your fields are just some scalar fields in Rn. So either you can think of that as one vector field, like with some index, but you know, the transport doesn't, n coupled scalars. And you have your Euclidean metric, and you have the most standard action. I'll just write the alternate. X, so let's say this dimension is D. You adjust this. And of course, now vectors, vector field. And so the name ON comes from a constraint that you put on this theory that you want the norm of these fields to be 1. So this is just the scalar product between this time is to be 1. So for example, if you have some spins or a spin chain system, you want them to be normalized in some way. So this would be like a nice condition you have, and that will describe this normalization. So you can put this right away in action as Lagrange multiplier. Right? This notation is the same as this. So that's one way to define it. Or the other way is that you just solve for this condition right away, and notice that all it does, it changes the target space to S and minus. It was really nothing.
Why don't you call the target space sigma?
Well, I usually
So the
Sigma.
space-time sigma. If you're the sigma model,
yeah, I was sort of using this notation to distinguish between the worldsheet and the space-time.
Yeah, but the worldsheet is now
Yeah. So I could do this. Right, so yeah, I mean you could use that, but now it's a space-time. It's not like a, because I think of a worldsheet as just some parameters, just some parameterization space or a space-time.
You can call it world volume.
Yeah, and yeah, I think of space-time as something that we live in, so we should have some.
Yeah,
So
but
actually, I think it's symmetric.
you're now writing down the sigma model. You're saying the action is a linear sigma model with a constraint.
Yeah.
So if you're thinking about it in that way, then sigma is the d-dimensional manifold. So it is the worldsheet. So if you're thinking about the notation, like sigma, source, state, target, worldsheet, you should somehow try to not mix them up.
Well, I do this because I always find it confusing when people talk about some theories and some actions, and they refer to them as the target space or as worldsheet action. And for me, this was always confusing, and I realized that people do it depending on where the space-time lives, either if it's in the target or in the source. So that's how I try to distinguish between what people would call worldsheet theory and target space theory, because this is what I think you would refer to as a target space theory, right?
Well, it's also a sigma.
Yeah.
Precisely a sigma.
Yeah.
So.
But it's a different than the string.
Well, not really.
I mean, this you would call
this is a D D minus one grain in living on the sphere.
Yeah, sure.
So it's just the same as the string.
Yeah, I always thought so too, but then people use these terms in a way that confuses me.
So, you know, if you're not by sigma models, I think that the terminology is world sheet or world volume and target space. That's fine. But then if you're doing just talking about field theory, where your fields does not have interpretations, coordinates, and manifold, then you can just take space time.
Yeah.
Okay, and then we're not talking about sigma models.
Yeah.
Even if it is a sigma model. So I think if you separate it in these two different ways, so volume, target space, those are all associated with sigma models. There's a sigma model somewhere. And if you are talking about just field theory, don't use the terminology target space. Use terminology space.
It's a linear sigma model, is it?
Yeah, because this
Before integrating the constraint.
So
It becomes nonlinear.
so the way that it's
Since it's constantly non-linear, right?
Yeah,
so it's in this product, right?
Okay.
So in this product, so I mean, you could write it as I'll use IJ, for example, and it's what you contract this with what metric you contract it with. Right? I contracted it with just the Euclidean metric.
Okay.
So I just wrote it like this, and that is an error model, but that would just be
Without the constraint.
without the constraint, but then the constraint makes it on the. And the equivalent way of doing this is just using the sphere metric, and then the Lagrangian now becomes. Yeah, I'll just write it. Yeah, it's just this. But now this dot is the spherical metric. So, for example, in the offering model, in so that is this is free, this n is free. You can use spherical coordinates, and then this will just be instead of using I'll just use the coordinates of the two sphere, the two angles. So these are equivalent. I just didn't want to write them in generic and dimensional, so I choose n equals 3. That's what this word means.
Shouldn't the integration be from till n, d rather than d? Shouldn't it be n?
Well, that just depends on
Shouldn't it be integrated over the Rn space?
no, I don't think so. This is the point of this sigma model stuff, is that you integrate over what this fields depend on, right? These files. So you have some coordinates x's here. They have some index I call them mu, and then this scalar fields phi that contains on this x mu, and you're integrating over what these fields depend on. So they depend on this axis, which is our coordinates here, and I just said that the maximum dimension is d of this. So I mean, it would not make sense to write an action where it's integrating over these files. I mean, yeah, I guess it could in theory make sense, but
No.
yeah, no.
A sigma model
Yeah,
just a theory of scalar fields, ordinary field theory of scalar fields, living on some space which is the world sheet or world volume. And they happen to have some interpretations coordinates on some other level.
yeah. Okay, so this is another example of sigma model, and the reason I chose to show it to you is that if the dimension, if d is equal to 2, then this model is integrable. I'll show you what this means later. It's also called no method classical back model. Of course, like it was debated, it's described as a Lagrangian, but then the meaning of the fields, which is a space of the system. And another model is called the principal chiral model. So here I will showcase the some properties of integrability, and this is defined as the target space is a group manifold. So that means that and the source is two-dimensional. It doesn't have to be, but I'll use a two-dimensional source space. So the map I'll call small g like a group element, so that's why I use big G. And then the group I will call, I will use big G here, but I just yeah, this is a group. I will use some calligraphic G. So yeah, this is the map. This is some group element. And the way that, so you would want to write down something that is like the derivative of this group element, but it's more convenient to use the Maurika forms. So you have the left and right Maurika forms, which have this Lie group value forms. And the usual notation is J for the left invariant one and K for the right invariant, Maurika form. And the fullbacks on the wall sheet are this. So that's just expanding this dg into using this formula that g depends on x and t, and I'll use the new coordinate for that. This is x mu. Mu is 1, it's like 0, 1, or 1, 2. And so this will be the main field of the theory. This is basically the pullback of the address on the wall sheet, or just coordinates of this platform. And since it's coming from the Maurika platform, it has a special, the second Maurika, or the second structure equations tells you that this is a flat connection, or that in other words, that this current J satisfies this equation. So later, and the sigma model action is given by. I'm using the constants from these papers I wrote down. So there's h bar over 2, and then there's a trace of these. Basically, this J contracted with itself.
The first one is not something like the torsion.
What do you mean the first one?
This?
Yeah, that will be a plus. If you have it with a minus, then plus this bracket, then there's the flatness. And I think torsion is just that this is.
Yeah, it's not like the torsion in coordinate basis.
Yeah, of course, it's very similar to that, but
No, I think it's not.
This
This
is
is
like-
the torsion is not really bad. It's also trick. But in a Lie group, you can choose if you want to have torsion and then curvature, or you can choose, or you can put curvature but not torsion. So the invariant thing is more like a equation, which is equivalent to this. In that equation, you can interpret one of the terms. The last one is actually either as a condition term, and then get curvature, or as a tension term, and then the connection is zero.
Yeah. But you can also view this as a standard signal model. So this, there's, you can look at this and you realize that this g to the minus first, and it doesn't look like actually here before. But you just expand this in the Lie algebra basis. So you assume there is some basis, I'll call it T, is a Lie algebra index of the Lie algebra. And then you just expand this vector field, so this one index called vector field, and you get something called the left invariant time field. So you can either use L or J. So these are just like the coefficients of the expansion. They have two indices. They depend on this. Yeah, M is correct. Yeah. And then we have D, where this phi is a coordinate on this group as a group manifold. So you think of this G as a manifold and it has some coordinates by M. So you can do this expansion of your field in these. So these are like the group coordinates, like manifold coordinates on. So these are the manifold coordinates of G. These will be coordinates on the Lie algebra, and this is the basis of the Lie algebra. So this is like an expansion into the time fields. And then if you do that, then this Lagrangian thing, if you do the whole calculation, just becomes X, where this G is just trace of these fields. So it's J R M J S M eta and this eta is the killing form. And so I think I don't have that much time, so I won't do the whole calculation. But we can do it afterwards if you want. You can just plug this in here and here, and then you come up with this. Sorry, this is Linus. That's for the right definitions of what the G is. It has this sigma model form. And this model has some nice property. It has some symmetry, which is that you can act with the group element from the left and from any group element from the left and from the right. And since these spherical platforms are invariant, then it has a global G times G symmetry from the left and right copy of the group. So either acting from the left or from the right. And the equations of motion are just conservation laws for these two symmetries. So the equations of let's go from here. So the equations of motion will be some conservation law equation mu J 0. You can have a look at the previous talk I had. I derived this by just doing a variation that like you would normally do. And
everybody sees that these are two different letters, right? There's also derivatives.
we didn't improve it much, but
I think the X went haywire.
yeah. And so another point I talked about this model that it is also integrable into dimensions. But here I'm just doing it. So now I'll do the second part of this talk and tell you what this integrability means and show you on this model like how you can see it, what it requires. And then I'll end with some more advanced review of what Linus has been working on and other people in this context of sigma models. So integrability, we'll start with what classical integrability or label integrability is. But so imagine you have some Hamiltonian systems with two n-dimensional phase space. So I mean some system where you have positions and momentum. And for this system to be integrable, you require a set of data, which is n quantities. So you require n quantities, which are all f, I, for example, so which have two properties. So they are in motion, which means that they commute with each other, so Poisson commute with each other, and that they are constants of motion. So they commute with the Hamilton. So you know that you can, in Hamiltonian formalism, you can write down the derivative by just acting with this Poisson bracket with the commutator. So if you have these n constant quantities and they are in motion, then you can play your system as integral, and then you can solve the system. So this is what you require. You require half of the dimension of the phase space. You have one constant quantity for thing, because h can be taken, for example, as f1 or f0, depending on where you counting from. So the Hamiltonian is already considered, and then you need n minus one more of these. And if you have them, you can solve the theory by so-called quadratures, which is a prescription for binary number of integrals. But the main point of integrability is how do you find these f's.
Well, so what do you mean solve?
I mean that there is a step-by-step process that you can do once you have these that will allow you to solve the equations.
What do you mean with, yeah, solve the equations of motion? So practically, what is the solution? I have confused the beam, so
Yeah.
Maybe Hamilton.
Yeah, you have some. Yeah, you just find a solution for the Hamiltonian. So some relation between these, which can be.
yeah, but what does it mean physically? I mean, I can understand mathematics, I guess, functions.
Yeah, you just solve Q's and P's as some functions of time. You will find what functions of time these are, or functions of time plus some relation between them.
Oh, which means that you get the phase space trajectory.
Yeah, exactly.
What do you get quantum mechanics? If you integrate, what does integrability mean quantum mechanics?
That you get the spectrum of the theory. You get, yeah, that depends. So when you solve it, then you will try to quantize the system and use this integrability. That's what it is.
No, I'm not saying, you know, but why am I interested in the physicist? I'm interested in making predictions for some system that I can measure.
Yeah, so it's like you would have no particle prediction.
So how can I see that? Why is that a constant solution?
Yeah, I don't know, I don't know, like, I don't know what that is. I mean, I think it comes from this involvement of these charges that you can, if you, there's another formulation, like Slack's formulation, for example, then you will see that the necessary condition for this involvability can be written by using something called this R matrix, and then the quantum X equation looks exactly like short particle production.
Sure, mathematics, everything. This is just an interesting, for me, question that's not answered very often in like introductory texts about integrability. Everybody sort of assumes that integrability should interest everybody. It's just great thing, but never explain like what it gives you completely. Also, involvability is more general than you look. So you require a bit more, or important that you have it to be zero, not proportional to f. Involutive set of objects that are in evolution, they commute to themselves.
I think because one of them is to be H.
Yeah.
So it will be 0 because one of them is this H. Right, so I mean, if you just have this, then you should just say it whenever condition is F.
Yeah.
But if you have this condition again, then of course this is
Really? Why?
or because they all no, I guess not. It just has to that this H, yeah, it's just deal with H, but the others can go with each other. Yeah. So I don't know what the result was zeros. I mean, so we also need them to be functionally independent, which is another condition, which I didn't state. I don't think this changes it to be 0. So that's like that you need this to be linearly independent. The functional and maybe this is just another way to get study. Yeah, I didn't question why this is real. Do you know that the answer?
No, I don't know.
So what was the quantum mechanical property from integrability?
I don't know.
No, in fact, I mean, you want to find, you have some distribution.
Sure.
Okay, so it was we involved in. Then by the probability theorem, if I remember well, it is also integrable. So this integrability means that you want to find those subspaces.
That's a different type of integrable. I think it's related somehow, but these two words mean different things. Integrable distribution and integrable theory. I think I related by this probability theorem, but it's a. I think it's a different like use of the word.
Okay, but you want to find basically the submental of the phase space where the equation of motion falls, right?
Yeah.
So,
But that's more.
no, but I mean, quantum mechanics is strange because you have this space as a space.
No, it's about having enough integrals of motion. So if you have some initial condition, you just calculate those integrals of motion. And since you know that they are fixed, any time evolution of the system has to keep these fixed. And if there are enough of them, there's no freedom. There's only one possible time evolution, and that's it. So that's the integrability in this case. And you could, I guess, imagine the same thing in quantum mechanics. So you have a wave function, initial wave function. From that, you could compute some constants of evolution, higher evolution, in quantum mechanics, and so using that, then the time evolution of the wave functions possibly also fixed. Like if you have an Eigen state of Hamiltonian, the time evolution is more or less trivial. So here you have it's an Eigen state of more operators with complete values. They don't change, so higher evolution is fixed. I don't know exactly how it would go.
Yeah.
You can do that.
Yeah, I think so. I've always seen it used in like constraining, scattering amplitudes, possibilities, and we don't need to calculate different diagrams. I've never seen it actually solve some quantum mechanical evolutions. So that I guess it would be what it could do. I'm not sure. I can check it on. But yeah, so the question is now how to find these Fs. Like if someone gives you a Hamiltonian, can you prove that it's integrable and can you use this integrability to solve it? So there is a trick called the Lex formulation of the Lex pair or Lex connection. Lex connection is in field theory as Lex pair is in both field theory and mechanics. So that is that we have your Hamiltonian system of Hamiltonian equations of motion, which can be some ordinary differential equation system, coupled with equations. And if you can find, so this is some equation, this is some ODE system, and then if you can find two matrices, usually called L and M, such that this equation is an equivalent, the ODE system is equivalent to this. So basically, what you want is to reformulate your equations of motion in terms of this matrix equation for these pair of matrices, which are tangent. And then there is a procedure on how to find these constraints and use this Lex formulation to your advantage. So to find these conserved quantities of constraints. And that is you create them by this simple formula trace of L to the power of 2m. So you power your matrix, you do L squared, L to the fourth, and so on, and you just generate these charges, these conserved quantities. So the proof is quite simple that this is conserved. You do so, this is conserved on shell, because that will be. By that I mean that it is conserved only if the equations of motion hold. Well, not only, but it is conserved if the equations of motion hold. So yeah, I'll just do a derivative of this. So I mean, it works similar to how we do derivative of functions.
Does it say trace or does it say T plus?
Trace.
In the equation above also.
Yeah. Yeah, so here I'm using a function to prove this. So I call table. So L dot is ML commutator. So I'll just write down two terms instead of writing commutator. Minus. And using the property of the trace, you can see that this is 0 because the first term is you can just multiply the L's together to write n times L to 2n. And the second terms, this trace and this cyclic property that you can do cyclic permutation of the matrices inside and it will not change. So I can move this to the left and I'll have n first and then L to n minus 1 and L on the right, which is also this. Because L's commute together, so I can just they commute with itself. So
Okay, so,
so we just move this to the left. And this is 0, so it's Q and is 0. And then you have these charges. And the question whether they are in motion or not is more complicated. So I'll just sketch.
So why don't you just use the Hamiltonian and the F's?
Yeah, I mean, you can, but maybe this is simpler in some cases. I guess integrability is not like you would want to do it all the time for any system, but for some cases, it is simpler than just solving the equation.
Is L supposed to contain all the F's? Or
Yeah,
just one of the F's?
No, all the F's, because this is an index which goes through this dimension of the phase space.
Why only even powers?
I guess. So I don't know. So this if so if okay, so if I just put some k here, I get k minus 1. I guess it will still work.
Well, this part of the proof is still works.
Yeah.
Something else doesn't work.
Yeah, exactly. Maybe so. Yeah, maybe it's needed for the involatility of these charges. So if you do a trace of L squared, then you can prove that it's the Hamiltonian, and I guess then you just need to do it again and again. And because you don't start at L1, L1 is not a trace of L doesn't give you anything. Trace of L squared, that's the Hamiltonian. And I guess then from that it goes by 2. So for example, if you have the harmonic oscillator, these matrices are given like this. That's for the harmonic oscillator. And
Wait, so now M is antisymmetric. So that's it? Oh, yeah, it's L.
yeah, this is the questions about these other things. And involatility is solved by something called the classical Young-Baxter equation, in which you introduce this auxiliary R matrix, and it helps you to decide whether these charges are equal to or not. That is quite a complicated topic, so I guess I'll skip it for now. And you can read about it and lecture notes, or you can discuss it afterwards.
So what is the dimension of L? Is it always?
Yeah, that's one of the points that it can be whatever you want, right? Or you just need that the system is equivalent. So for example, for this harmonic oscillator, if you do the commutator, you will get the harmonic oscillator equation in both of these slots of L dot. Like of this equation, it will hold in these both diagonal slots, so it will have like two equations at once. But you could have some 4 times 4 matrix and have the system.
Yeah, but you probably, if you want to have n conserved quantities,
Yeah.
then the dimension of the matrix cannot be less than n or something, because if you take, if you have an n by n matrix, if you take L to the n, higher power than that, you can start to write them in terms of lower power.
Yeah, okay, yeah. I guess there is some constraint on. But I know that you can have more options on how the matrix, how big is the matrix. But maybe there is some lower bound. I guess. But it should be possible to write it more different ways. There is some gauge freedom in this choice. That can be parameterized somehow.
So, so the only conserved quantity for the harmonic oscillator is the energy.
Yeah,
So only one G.
yeah. In this dimension. Okay. So, yeah, you can do something similar in for a field theory. So if you have 1+1 dimensional field theory or a sigma rule to discuss mechanics. Now we're going to field theory. So you always needed some certain number of these conserved charges. But in this field theory, you need infinitely many of them. So you need some way to generate infinitely many conserved charges. So the way you do it is by expansion in some auxiliary spectral complex parameter. So that is some complex number. And it just serves as a way to generate these infinitely many conserved charges by means of a Lorentz expansion. And so what you need is, so again, this is the same as this Lax formulation. You want to formulate your theory in terms of this Lax connection, and it has to satisfy this flatness condition. So I have 1+1, so I have two coordinates. And then you will get, you can construct some object from this LX. I'll just do this very quickly, which is important. You can have it later. I'll just show you how we can generate these charges. So you have this part of the exponential of this integral. And then if you do expansion of trace of PZ, we do Lorentz expansion, so in the Z, then you will find these charges. So this will be the concept. You can prove it by doing derivative of this, and then prove it, then doing the derivative of this integral, and proving that using some nice boundary condition it has to be 0. So I did that in the previous talk. So you can have a look, or it's in the.
May I ask, what about the arrow about the text?
Yes, so that's ordering of the exponential because these are matrices, so we don't have to commute. So you have to choose some special ordering. Okay. And this is like for this part. Okay. And when you're doing the exponential by doing the expansion of the exponential into 1 + x squared and so on, and then the computation of the matrix. So now I will talk about the integrability in these PCM models, and then I'll just end with more conclusions. So going back to this PCM model, how you can see that it is integrable. So this was the PCM model, and just for coordinates, I will go to Python coordinates, in which it is simple to write. So I'll use x plus minus. So this action then becomes just j plus j minus. And what you do is you use, if you have this action written in this principal chiral model way, then you need two properties of these J's to be satisfied for you to define Lex connection. And the first one is that it needs to be flat. And that is from the Maurer-Cardano equation, so that is fine. Plus, plus, minus 0, and then it needs to be conserved. I'm talking about this J, this current needs to have these two properties. And if it does, then there is a standard way of proving the integrability. And that is, you can construct this L, this Lex connection, by just dividing this J plus minus with this spectral parameter Z, which is with this complex parameter, and then you can do this expansion to find the conserved charges. But the point is that if you have some theory which is of this type, and your J satisfies these two equations, then you can find the Lex connection and do these similar tricks like we did here, and the theory is integrable. So in the previous talk, what I talked about some sort of more complicated version of this is that one of the first things Linus did, or maybe this was even done before. No, I think he was working on this, and that is that you can take another model, a different model, so some sort of deformation of this, called the Young-Webster deformation, and you can change this action, this Lagrangian, from trace J plus J minus to trace of J plus, and then you deform by some operator R, and this is just some deformation parameter, which when you take it to 0, you get the geometry, and you get a completely new theory. But you can calculate again the equations of motion and the symmetries and everything like that, and then you find that this relationship between this L, the integrability, and these two conditions is generally for these types of models. So if you can, in this new theory, find a new current that is also flat and also conserved, you will be restoring, you will be proving that this deformation preserves integrability. And you can do that quite easily. You define new J, this is big J, by this formula. So G minus this is just J plus. Oh, this is the other. Oh, this is just J plus. And similar for the J minus. And they will satisfy these equations, but not now for the big J. So you have deformation here, but if you can still prove that the flatness and conservation are still there for some new current, it can be some new current, then the Lex formulation still works and it is still integrable. So that was one of the works that Linus did. So this was known before, and he showed another way of doing this for this PCM, and that it is related to just doing the T-duality. If there's some specific, you add some different deformation by some co-circle, and if you do T-duality, then it is equivalent to this deformation, and T-duality is known to preserve integrability. So that is another way of proving this Young-Webster deformation preserves the integrability of this model. And then another thing was working on was this preservation of integrability, but for the string sigma model. So the string sigma model, I have told you if it is integrable or not, and that depends on the background fields that you have on the metric and B field. So it will have to have some special background, special space in which it is integrable. Some of the examples are AGS5 plus S5, or these maximally supersymmetric solutions also are legitimate. But this deformation has this nice property that it preserves integrability, but even if you start with a model that it is not integrable, you at least generate new solutions in supergravity. So either if you have integrability, it gets preserved, but if you don't have it, you have a solution generating technique. So it does not change. It doesn't change the supergravity equations. So you get at least new solutions. And I mean, if it is given by, or if you have the string sigma model, there's some background G being fine, and the prescription for this change is written by. So this is like change in G minus B. 1 plus eta times theta, and B minus B minus first. So something like very similar to this, where this theta is because this space-time indices, so and then in the same the algebra indices. Where this R is the same operator, this R matrix is before, and this case has some isometries. So normally I introduce you this ambidextrous deformation only for this case of the PCM, but you can do it also in the string sigma model, but you need something more, and you need that your background is isometries. These are just the killing vectors of the matrix. So isometries, you have some killing vectors, and you can construct this space-time metric Ij by constructing this Lie algebra. So the R matrix is now like sort of the algebra. It deforms the theory, and this preserves integrability because of this special. This R matrix is pretty special in some way. And what we also did together was to check. We know that this preserves integrability of cells and solution generating techniques, but we are concerned about how does this work in the quantum corrected versions of gravity. And this preserves while invariance up to like quantum corrections to the second rule. And for that we use something called double field theory, which is quite natural with this formalism. So here you can see the G and D fields are sort of grouped together. You don't have a description for G prime, S, and B prime separately because they're together in a sense, and you can make a new formulation of supergravity in which they come together with generalized field, and then it's much easier to write down these deformations, and you can check much more easier that they preserve the equations of motion up to all orders in the quantum corrections. I think that's everything. So just to summarize, I've shown you some of these models, like this string sigma model and this PCM. They are nice to showcase some basics of integrability. And what me and Linus and other people have been working on is more in terms of these integrable deformations. So that is doing some change of this Lagrangian and seeing how this change has to look like for the integrability to still be preserved. And in the string setting, you are interested in the equations of supergravity. These are this target space, and if they are preserved under this, and up to what order in quantum corrections. And for that we use a different formalism in which it is nicer, and it's related to this grouping of G and B together. So if you're interested about some parts of this, some different calculations, or you want to do something, do some calculations like this, you're free to check out the previous talk I gave or these two lecture series, or some other lecture notes I can give you. You can just ask me, or we can do it together, some calculations. Okay. But you can also check out Linus' papers on this topic to see if you understand, and what, you know, it might be able to give some interaction for you to be able to read the paper. Yeah, but okay, that's all right.
Thank you.
So please feel free to ask something. Something was not clear, or you want to know more about something.
Yeah, like I might take some time to take my time to take a look about PCM because I'm not too comfortable with that. Also,
Yeah.
taxpayer formulation, like I might try to go through the calculations. So
Yeah, I mean the lifestyle is most relevant to this mechanics stuff. For these field theories, you just need a connection that is flat and constant. And in this PCM, you have it right away, just from the equations mentioned. And then if you deform it, you're just checking if you deform the flatness or the observation, and if you can make a new one that is flat and constant. So, you know, this Lexpert formulation is more for the mechanics side, and then this connection, Lex connection formulation is for this field theories. But yeah, this exactly is done in this translation. And then that serves as like an introduction. He basically then reviews what Linus did in his papers. I think it was 5 years ago or so. 6 years.
Also, when we, but say we have found this FIs, so and say we do this canonical transformation on our phase space variables Q and P, change it to some other.
Yeah.
Our Hamiltonian might change to some.
Yeah, it will diagonal analysis.
Those same Fs will work for the new Hamiltonian as well.
Yeah, this canonical change is called action angle variance. So that's exactly how we would do this procedure of this solving this using these conversions. That's by using these Fs as a new these are also in motion, and you will then to change the structure levels to basically diagonalize the Hamiltonian to this action angle variance. Then we can read the solution. I mean, we can then see the solutions much easier. Feel free to talk to me if you want.
the other question guys like to go to that something.
Yeah, okay, no problem. Well, we recorded it.